So we know how to find SIFT features in an image. We also know the size of the image. We know how to undo the effects of scale and orientation or rotation. What we need now is some kind of a signature that you can compute from a SIFT feature so you can match it with other features. So let's talk about how we do that. So imagine that this is an image that's given to you. You apply your SIFT operator, and then you end up getting these SIFT features. And this happens to be one of them. Let's focus on this one. Well, we know how to undo the effect of rotation by computing the principal orientation. We also know how to undo or normalize for the scale itself. So we can now take the content that's sitting in here and place it on a grid of some size, some standard size right here. That's this grid you're looking at. We also know that we can compute the gradient at each pixel, in both in terms of magnitude and orientation. But what we're going to do, as we did before with the principal orientation, we're going to ignore the magnitude because that's sensitive to the lighting and other effects. We'll just preserve the orientation of each edge in here. Okay, so now we're going to do the following. We take the first quadrant here, this quadrant, and we're going to compute an gradient orientation histogram. That's this. So these are all the different directions, and these are the number of pixels that have each of those directions. That's a histogram. And then we're going to take the next quadrant, this one, and then compute another histogram, and the third quadrant, and finally the fourth quadrant. And you're simply concatenating these orientation histograms together to create a long histogram, one histogram right here. Now remember that this histogram is normalized in the sense that it is invariant to rotation. We already have undone the effect of orientation or rotation. We have undone the effect of scaling. And by ignoring the magnitude of the gradient, we are also less sensitive to brightness. So this is something that we can directly use as a descriptor, a signature for matching two SIFT features. So how do we compare two SIFT descriptors? That's very easy. We can use a few different metrics for this. One simple one would be the L2 distance between two histograms. And so this is the first histogram, the second one, you subtract them bin for bin, square them up, add them up, that would be the L2 distance. And of course, if it is 0, then you have a perfect match. Another way to do this is by using normalized correlation, when we talked about this in the context of template matching. So this is the first histogram, the second histogram, you're subtracting the means here, and you divide by the energies of the two histograms, and if the normalized correlation is 1, you have a perfect match. And here's one that I want to throw in here, which is called the intersection metric. Very useful in many different contexts. So in this case, you have these two histograms, and you're basically going to find bin for bin the min between the two histograms. That's really computing the overlap between the two histograms. And you add that up, and you end up getting your metric right here. So the larger the value of D, the better the match. So now let's take a look at how the SIFT detector works with images of objects. First, we're going to take a look at scale invariance. So these are images of the same object, but different scales, different magnifications. And each one of these lines that you see here corresponds to a successful match. So this is a little bit hard to see because you have lots of features and lots of matches, but you may want to just freeze the video right now and take a look at these matches, and you'll find there's a lot of very good matches here. Here's another example of another object, also plenty of matches. And given that you have so many matches, you should be able to then use these matches to recognize the object, as you can imagine. And now let's take a look at rotation invariance. An object and a rotated version of the same object. Once again, you can see a lot of good matches between these two images. A little bit more rotation. This was about 45 degrees. This is 90 degrees. And in this case, it's upside down, and you're still managed to get lots of good matches. And here comes the big one, which is robustness to clutter. If you remember, we said that occlusion is one of the really hard problems in vision in general, but particularly object recognition. And so in this case, you have this object, and here the object is partially occluded. But whatever features were recoverable here from this object, you're able to find them in this object right here. And it doesn't have any mismatches with other objects. So that's really important. So you're recognizing the object in part, and that's all you can do when you have occlusion, and that's good enough for actually finding the object. Here's another example. This object is at a completely different scale, also partially obstructed, but quite a few good matches. And here is an even more challenging case where you have this object right here, partially visible here, and you can see that this is the orientation of the object that we were able to recover, and the scale as well. Now let's take a look at some other applications of the SIFT detector. Here is one which is very popular, which is stitching images together to create a larger image or a panorama. We are going to devote an entire lecture to this, and that's actually the next lecture. However, let's take a look at a simple case here. You have two images, and what you do is you first find SIFT features in both the images. And then you use the descriptors to match features, and you see that these ones match right here. And based on these matching features or correspondences or pairs of features, you're going to then essentially take one image and warp it and align it with the other image. This process of warping requires a geometric transformation, and we're going to talk about it at great length in the next lecture. But for our purposes here, imagine that such a transformation is possible. You warp them, and then you overlay them, and you get an image that looks something like this, a larger image. We'll also discuss in the next lecture how we remove these seams and make it a completely seamless panorama. The same thing can be done to construct collages. So here you have a large collection of images. You simply apply SIFT to each one of these, and then you match features among these different images, and you can bring these images together to create a single collage with a much wider field of view. So we've seen that the SIFT detector and descriptor can be used to solve a variety of visual matching problems, and we showed how it can be used for recognition as well. So does that mean that the general problem of recognition of three-dimensional objects can also be solved using the SIFT detector? Not really. So the kinds of objects we've been looking at thus far are more like this. They're planar objects, perhaps with some complex appearance on them, but they are planar objects, which are moving around on a plane. They may be rotated, they may be scaled in terms of magnification, perhaps even some occlusion and differences in lighting. But when it comes to 3D objects, things start getting more complex. So for instance, you looked at this object right here. If you look at it from this viewpoint and then from this viewpoint, the local appearances of these different features are going to be very different. So if you applied SIFT to two images of such a 3D object seen from different viewpoints, you will indeed get lots of features, but the descriptors are not going to really match. At some point, SIFT is going to fall apart. So let's take a look at when that happens. So here you have two images that are taken from roughly the same viewpoint. And as expected, you get lots of matches. Each one of these lines, once again, is a successful match. Now imagine an image taken from some angle and another image taken from roughly 30 degrees away. So you get these two images. And all of a sudden you see that there is a sudden drop, a dramatic drop in the number of matches between these two images. And if you keep going, as you would expect, here you have a 90-degree change in viewpoint. You hardly get any matches at this point. So all this to say that SIFT is reliable only for small changes in viewpoint. But that said, it still is an extremely useful and widely used detector in computer vision.